Welcome. My name is Chuck Ridgway. I'm the Automation Technology Manager here at Horner, and we just want to welcome you to another live stream. Today's topic is one that we think will be great for new users. It's getting started with Horner OCS. You know, here at Horner, we try and create content for our advanced users, for folks who've been using our products for some time, but also we like to create content for those who are a little bit newer. And this is one of those days. So we've got a great program for you all about getting started with OCS. Let me go ahead and bring in Mr. Casey Gardner. How are we doing today, Casey?
Hey, not too bad. How's it going, Chuck?
Very good. So like I was saying, a lot of the content we try and create is for different levels of users. Today is really all about those who are just getting started with OCS.
Yeah, and as a new user, one of the first questions they might come across is what is an OCS, first and foremost? So, um, at Horner, we're kind of known for our all-in-one controllers, which give you a flavor of graphics and logic, kind of all in one package, as well as some onboard I/O. And using our Seascape software, we actually have it available to all of our different series, all in the same software, where it gives us both the logic and graphics design all in one. And hopefully, this presentation will go into a little more detail for that.
Yeah, that's something that we really take pride in at Horner is the fact that we have one software package for programming any of our controllers. And I know that Casey has a lot of experience in kind of walking, especially new OEMs. You know, one of the key parts of Casey's job, and mine as well, really, is for new customers, new OEMs that are designing machines around our products. They usually need a little bit of help in what we call onboarding. And this sort of material we're going to be presenting today is the type of thing that sometimes we present to those guys. So anyway, we hope everybody enjoys the presentation. Now, I will say this, though. I have a confession to make. We're not 100% live today. Now, Casey's live. Casey's standing by, watching the chats, answering questions like always. I'm on vacation on a beach somewhere. So enjoy the presentation. Casey's going to take great care of you. I'll see you when I get back from Miami. Take care. Okay, getting started with Horner OCS. Let's get started. Okay, in today's session, we're going to cover the following topics. We're going to start with model selection, followed by software setup, making a connection, configuring hardware, programming logic, and building screens. We feel like with this head start, you'll be able to become real productive when you use your OCS on your first project. Let's take a look at model selection. This isn't intended to be an exhaustive comparison between all the different OCS all-in-one controllers, but a quick reference for you. We've got 4 primary product groups that you can see here. Let's start with the Micro Series. There's 3 models in the line currently, ranging from the 2-inch key-based model X2 up to the 4-inch and 7-inch touchscreen versions X4 and X7. The Micro Series is best for simple applications. It's got a slim design, it can support up to 5,000 logic variables, and it has 2 built-in I/O options ranging from 26 to 30 I/O. Now it doesn't support CAN Open or J1939, and it also does not support MQTT IoT protocol. Moving on to the XLE and the XLT, for years, these were the entry-level products for the Horner product line. But now that the Micro Series is available, they've moved up a little. These products offer great control with a basic user interface. They can be DIN rail mounted, which means that if you're really just looking for more of a PLC without a significant user interface, these products could be right for you. They support double the amount of logic variables that you'll find in a Micro Series, and they have more flexibility in the built-in I/O with up to 5 I/O options ranging from 22 to 42 total I/O points. They do support several of the protocols the Micro Series does not, including J1939 and CAN Open, but the XLE and XLT do not support MQTT. Now for the mainstream XL series. This is our most popular product line, with touchscreens varying from 4-inch to 15-inch. They support a whopping 50,000 logic variables, and they offer 5 I/O options, just like the XLE and XLT, although with some of the options, the resolution of the analog is higher. Also, for the XL7, EXL10, and XL Plus, you get dual Ethernet and dual CAN. And the 15-inch XL Plus expands the audio-video features to full screen. Finally, let's take a quick look at a couple of our specialty controllers, the X5 and the RCC. These products don't necessarily fit in one of our standard product categories, but they're great products nonetheless, just not as popular. The X5 offers a unique combination of features with a form factor similar to the Micro series, but processing power more similar to the XL series. RCCs are just like an OCS, just no screen. And the RCC 6512, that's got a little bit of co-processing and a lot of high-speed counting. Now, software setup. In order to start programming your OCS All-in-one Controller, you're going to need to download Cscape. It's free, but there are some requirements. First, you'll need to register at our website. Next, you'll need to log into the website, navigate to the Cscape download page, answer a couple of simple questions, pick out the specific Cscape version you'd like to download, and then download the install package. Here's my Cscape install file after I unzipped it and moved it to my desktop. You do have to be an administrator to load the install file. Let's get started. We'll fast forward through a good part of this stuff. Next, let's make a connection between Cscape on our computer and our new OCS All-in-one Controller. Okay, the controller I'm going to get started with today is the Micro X4. And I've got one powered up here through 24 volts. It's now face down on the table, and I haven't connected it yet to my computer. Before I do that, I want to make sure that Cscape is looking for the right target ID for the controller. Now, every OCS ships from the factory with a target ID of 253. That happens to match the C-scan ID. Now, if we look down here in the lower right-hand corner, it shows we have no communications, which makes sense because I haven't connected my computer to the OCS yet. But it also shows target 1. We don't want target 1, we want target 253. So to change that, we go up and press the little target icon and set the target for Cscape to look for at 253. It's asking if we want to open hardware configuration. I say no. All right, so now at least we're looking for the right target. But keep in mind, I haven't plugged in my USB cable yet. I'm going to go ahead and do that now. Now, the first time you plug in your USB cable, what is likely to happen is that Windows will busily load the communications driver so it can talk to the OCS. Now, in my case, the communication driver was already loaded. Now, I still don't have communications. Let's actually go take a look at Windows and see if we can find the OCS connected to one of the COM ports. I'm going to select the device manager and look for ports, COM and LPT. Let me expand that section, and there we go. USB serial device, COM8. Okay, so that's the COM port that the OCS is connected to. I'm going to close down the device manager and go back to Seascape. Now let me go to the controller menu and connection wizard, and I'm going to select USB. Now oftentimes with Windows 10, it doesn't find the port on the list here. If that's the case, no time to panic. We strictly go back to serial, because remember, USB stands for Universal Serial Bus, and we can then manually fill in COM8. Now for many of you, COM8 will show up under USB like you'd expect. But for those where it doesn't, you can follow these steps. Okay, I've hit finish, and down here in the lower right-hand corner, sure enough, local 253, target 253. Let's configure that OCS. Okay, back to Seascape. To configure the hardware, we have a couple different options. We need to go to the hardware configuration section, which we can do from this little icon here, or we can go to the controller menu and select it there. Okay, now one thing you'll notice is that by default, because this OCS was not connected when I started up Seascape, it still is using another controller as the configured controller. Now, if I would have had the X4 connected and it was talking right away when I connected Seascape, Seascape would have automatically selected my micro X4, but it didn't. So I'm going to go ahead, and I've got a couple different options. One option is I can manually find the micro OCS here, and this is what I would do, for instance, if I didn't have an OCS and I just wanted to program offline. Okay, so I could select micro OCS series here, and then I would select the model, which in my case is an X4. All right, it's going to give me a warning that the total number of screens that are available to program in this unit is 250, which happens to be less than what was on the XLE that was previously configured. So that's why I got that warning. I'm just going to hit OK. And then I have my choice between the X4R and the X4A. And I happen to have the R, as you can see from my inset there. Okay, so I could basically use that method for selection, or I could go ahead and hit the auto configuration button. Since I am talking local 253, target 253, I'll hit auto configure. Okay, again, it gives me that same screen warning, and it selected automatically the correct controller. So that's the first step in the configuration process, selecting the right controller model. Next, we need to configure the built-in I/O. To do that, let's go ahead to the local I/O tab. Okay, here you'll see kind of a side view of the controller, and you have the option of hitting the config button. All right, that shows you the I/O map. Now, there are 4 different types of built-in real-world I/O in an OCS controller. You have I for digital input, Q for digital output, AI for analog input, and AQ for analog output. And these are the default number of each of those memory types that are configured to the controller for the built-in I/O. All right, now to set up the individual I/O, let's go to Module Setup, and you'll see 4 different categories: digital in and high-speed counting, digital out and PWM, analog in and analog out. All right, let's start with digital in, high-speed counting. Now, in applications where you're not doing any high-speed counting, the only thing to configure is whether you want positive logic on your digital inputs or negative logic. Remember, positive logic is where you run a positive signal, say 24 volts, into the digital input. And then when it sees a high signal, then it will turn on. Negative logic is when the input is actually looking for 0 volts in order to turn on. Okay. Now, if you do have high-speed counting in your application, you've got up to 4 high-speed counters that you can allocate. Let's talk about that next. All right. By default, they're disabled, as you can see. Let's start out by taking a look at the options for input number 1. Okay. I can count frequency. I can totalize or count positive transitions. I can basically measure the width of a pulse, or I can connect a quadrature type signal like you might get from an incremental encoder. So those are my options. Let's say, for the sake of argument, that I'm just going to be counting pulses on high-speed counter input number 1. So I'll select totalize. It's asking, what am I going to count? Almost all the time, you're going to be counting the rising edge, which is what I want to select here. Okay. And if you just want to count inputs without any maximum, if you will, and just reset elsewhere from, let's say, a digital input that's internal, that's assigned to that counter inside your logic, then you typically would leave that at 0. The only time you're going to set that to some non-zero value is if you are using an encoder, and in the application, it's a rotary application where there are a maximum number of counts per revolution, and you only have exactly 1 revolution for your mechanical system. If you have more than 1 revolution, you'll still leave that at 0. Okay. Other options include pulse width, where you're measuring the width of a pulse, and quadrature, that's where you're typically connecting an incremental encoder. For an encoder, you're going to select the style. Do you want the first encoder input to lead the second? That's by far the most typical. Or do you want the reverse? We'll just go ahead and select 1 leads 2. For more information on encoder applications, you can see our webinar or our pre-recorded video for encoders. Okay, so that is a look at high-speed counter, but I'm just going to go ahead and start by disable. In my application, let's say there is no high-speed counting. Next, let's take a look at the digital outputs. All right, now for most applications where you're not doing any high speed on your outputs, things such as a PWM signal, for instance, or turning an output on in reaction to reaching a specific encoder input position, in those applications, you're just going to leave the 2 high-speed outputs at normal. Okay? And that's really all there is to it. The other option you have with the X4R model, remember, it primarily uses relay outputs, and there's 6 of those. However, there are 2 high-speed solid-state outputs. And for each of those, you can configure whether those are wired as syncing or wired as sourcing. Now, keep this in mind for the X4R model, or any of the R models for the Micro series. If you wire the output as syncing, you have the ability to drive 0.5 amp on the output side. If you wire it as sourcing, you're only going to be able to drive maybe 50 milliamps. So there's a big difference there. So if all you're using the output for is to drive a high-speed output, syncing is almost always going to be the better choice. And frankly, it's going to be the better choice unless the amount of the load that you're driving is very small. Then in that scenario, you could select sourcing. Okay, so in addition to those selections, the only thing that's left is to configure what happens to your outputs when the controller goes into stop mode. And 99% of the time, you're going to leave that at default so that when the controller goes into stop mode, all the outputs turn off. But in that rare occasion, for that rare application where you want different behavior, you have the ability to make an output turn on power down, or to hold last state on power down. But again, 99% of the time, the default of off is going to be where you want it. Okay, next let's take a look at the analog inputs. There's a little bit of configuration we can do here. By default, all 4 analog inputs are disabled, and you want to go ahead and configure those for a different range if you're actually using it. Now, in the case of the Micro X4, you have your choice between 0 to 20 milliamps, where 0 counts is 0 milliamps, and 32,000 counts is 20 milliamps, 4 to 20 milliamps, where 0 counts is 4 milliamps, and 32,000 counts is 20 milliamps. Now, if you do have a value below 4 milliamps coming in, let's say because your sensor, for whatever reason, is disconnected or reading quite low, you will still get a negative reading that will tell you that you've got an issue on that sensor. Either it's low or it's disconnected. So almost always, for the best resolution, 4 to 20 milliamps is the better choice. And then finally, you can select RTD PT100 on each channel. Now keep in mind, with the Micro series, this is a limited range for RTD. Normally with RTD PT100s, the full range would be, let's say, -200 to +850C. But with the Micro series, because it is a budget line, you are limited to a temperature range of -50C to +200C. But for a lot of applications, that's perfectly fine. Okay, so you can select the signal that you've got on your analog inputs, and each one can be set independently. Okay, and then you've also got what's called this filter constant, which you can set between a value of 0 and 7. And this is effectively a setting that will allow you to make a selection or a compromise between fast response and steady readings. 0 means there's no filtering, so every scan, the controller is going to take the analog to digital conversion and report it directly to the analog input register. If you set it to a value of, say, 7, which is the maximum value, it means that it will take the current A to D reading and weight it 1/8 between that reading and 7/8 between the current average. So effectively, 7 is your maximum setting, which means that you're going to have the smoothest signal, but with the slowest response. Finally, there is a configuration register for advanced applications. If you want to change the sensor type on the fly, then you could select a variable here. You could allocate a register here, and you could, on the fly, decide how you wanted each of your 4 analog input channels to be configured. But let's leave that alone for now. Okay, finally, let's configure the analog out. And really, there's not much to configure on the analog output side besides whether you want the channel disabled or you want 4 to 20 milliamp mode. Okay, once you've configured that, then you can decide when the controller stops, do you want it to hold its last value, or do you want it to say go to a value of 0? Okay, so most of the time, you're going to want the value to go to digital 0, which is equivalent to 4 milliamps, if the controller goes into stop mode. And once again, for those advanced applications, if you want to assign a variable here, you could, and then you could make these configuration changes on the fly. Okay, so that's a look at the I/O configuration. It's time to start programming logic in Cscape. Now, before we dive into programming logic, let's take a look at the OCS memory structure, which is an important concept to understand before we start programming. As I mentioned in the hardware configuration section, there are 4 different types of real-world I/O memory. Those include I's for digital inputs, Q's for digital outputs, and then a couple of word types for the analogs. AI for analog inputs and AQ for analog outputs. In addition to that, there are also internal memory types. %T or temporary, non-retentive bits, %M or maintained for retentive bits, and then some general purpose word type registers, %R, which are retentive 16-bit words. There are also a couple of special memory types with predefined values. There's S, system bits, and SR, system registers, which again are 16-bit words. So that's the OCS memory structure. As we prepare to write our first bit of logic, I want to mention that there are 3 different options for programming logic in Cscape. Advanced ladder, which is register-based, advanced ladder, which is variable-based, and IEC 1131. Now, for the sake of this getting started, I'm going to go ahead and use the most basic, and that is advanced ladder that's register-based. We have plenty of other resources online to show you the other programming styles. Okay, let's say we want to do a simple ladder logic program. What you've got here with Cscape, and this is the default setup, by the way, is you have your programming environment here. You have your project toolbox here, all the different types of instructions you can use for advanced ladder. And then you have what's called your project navigator here, which is one way for you to get around your program and navigate to different sections of the configuration. But we're not going to spend a lot of time on the project navigator today. Let's get started by just writing a very simple start-stop rung. Okay, you'll also notice in the center section here, I have some of the common elements that are often used with ladder logic programming, including a normally open contact. So I'm going to click on one here, and I'm going to drop it in column A by clicking. Now, when I did that, you see that a screw head appeared, which indicates that a rung has been started. Now, it doesn't really matter where in column A that I clicked. Okay, it's going to start the rung there. All right. Now, once I've done dropping the contact, I can either continue to draw my logic by dropping another, I can change to a different element and draw that, or I can go back to my pointer device and I can double click on the element I just dropped and configure it or assign it a memory address. Let's do that here. Okay. Now, with register-based advanced ladder, for every variable you create, you need to assign its memory address. So in this case, let's say that this contact I just dropped is part of a start-stop circuit, and let's say it's a hardwired start push button. Okay, and let's say it happens to be wired to the 5th digital input point, I5. Well, let's go ahead and type in %I5 here under the address, and then we can name it whatever we want. And in this case, I'm going to call it start_push button. Now you'll notice I use underscore instead of a space character or a dash character. Those 2 characters are not allowed for names. Okay, so I've created a start push button contact. Now let's say that when I press the start push button, I want to turn on a motor starter, which is a coil. Okay, so I'm going to select the coil, and then I'm going to drop that somewhere over here on the right. Now in Cscape, you can have programs up to 30 columns wide, going all the way over to column AD if you want. Okay? In my case, I'm just going to go ahead and drop this coil, let's say somewhere around, let's drop it here. It doesn't really matter. It's just going to need to be the rightmost element on the line. So I'm dropping it here. I'm going to go ahead and go back to my pointer, double click, and I'm going to assign it. Now let's say it's connected to the first digital output, okay, which is Q1. Now you noticed in this case, I didn't type the %sign. Most of the time, you don't have to actually type the %sign. If you just type in Q1 or R1 or I1, Cscape knows what you mean. Now under name, I'm going to give this a name. I'm going to call this motor starter. Okay, hit OK. All right, so I've created some basic logic, which basically says when I press the start push button, the motor starter is going to turn on. But for any of you who ever use ladder logic, you know that this isn't going to work very well, because as soon as I let go of the start push button, my motor starter is going to turn off. And that's definitely not what I want, right? Okay, let's go ahead and seal around the start push button so that when I release it, the motor starter will keep going. Now, that means I need a parallel contact. All right, well, how do I do parallel contacts in Cscape? Well, we have the vertical branch tool here. So I select that, and I'm going to click underneath and to the left of the start push button, and then either right here exactly or just somewhere over to the right, I'm going to put another branch. I'll go back to a normally open contact, drop the normally open contact, go back to my pointer, double click. Okay. Now, for a seal contact, we want to use the motor starter as a contact, which is Q1. So I could just type in Q1 here. The other option is I can pull it off a list if I don't happen to remember what I had named it. Now, it's right above there, so I'd be, having a pretty bad day if I didn't remember what that was called. So let's go ahead and select it from the list to show you that I can, and I'll hit OK. All right. So now when we press start push button, the motor starter will start, and we'll seal around it so that when we release the start push button, the motor starter will keep going. But as you've noticed, wait a minute, I have no way of stopping my motor starter. So let's grab a normally closed contact as our stop button, okay? And let's go ahead and assign it its address. Okay, now in this case, let's say it happens to be the third digital input is wired to the stop push button. So I'm just going to type in I3. I could also select %I3. Heck, I could even type in 3i if I wanted to. Cscape is happy with all that. And in this case, let's call it stop push button and hit OK. All right, we've now configured our first rung of ladder logic. Basic, yes, but it's now configured. Let's add some more to our example. Let's say that we want to time how long the motor starter is running, and then let's say after 10 seconds, we're going to turn the motor off again. Okay? Don't know why we would do that, but let's program it to do that. Okay, so I want to start off with, again, a contact in column A would start a new rung. Now, if I don't drop the contact in column A, let's say I put it here, all right, you notice that a new rung did not automatically start. It doesn't mean I can't put it there. It just means I have to manually start my rung. And I can do that. Let me switch back to the pointer button here to make it clear. I can do that by right-clicking here in this area and pressing New Rung. Now I've got the screw head, which is our indication of a new rung, and I've got the contact I've just dropped here. And let's go ahead and assign it while we're thinking about it. Let's make this the motor starter, because that's what we want to detect and start timing. All right, now how do timers and counters work? First of all, where do we find them? A couple different places we can find them. Down here in the toolbox, you can look under timer counter operations, but they're also listed here in the center convenience area. So I'm going to select a timer, and I'm going to go ahead and drop it there and go back to my pointer. All right, now, how do timers work? Now, with some PLCs, and the OCS is a type of PLC, you have special memory address types for timers. The OCS isn't like that. The OCS just uses general purpose word type registers for timers, and it uses 2 of them consecutively. So if I were to type in %R1, remember I don't have to type in the % sign. I'm selecting a general purpose register with my R type, and I happen to be picking number 1. It doesn't really matter which one I pick. All right, I'm going to pick number 1. And what's going to happen here is what's actually going to be assigned to the timer. R1 is the first 16 bits, and that's going to be my accumulator, which is timing or accumulating a time value. And then the second 16-bit register, which is right next to it, R2 in this case, is going to be used for a housekeeping register. Okay? So every timer that's a 16-bit standard timer is going to take up 2 consecutive word type registers. So in this case, I assigned R1. That means R1 and R2 are being used for this timer. All right, and I can go ahead and give it a name if I want. I'll just call it a starter timer. All right. Now, this can either be an on-delay timer or an off-delay timer. It can delay turning on or delay turning off. We're going to go ahead and make it on-delay. Resolution can range anywhere from 1 millisecond all the way up to 1 second. Now, let's say that we want to time the motor starter running, and I think we said 10 seconds, right? So I'm going to set my preset value to 10 seconds, and in 100 millisecond counts, that is a preset value of 100. So when my accumulator reaches a value of 100, my timer effectively will have timed out, and it will pass power flow from the left to the right at that point. Okay? Now, if I want my timer to remember its value through a power cycle, or effectively to have to be manually reset, then I will make it retentive. If I just want it to clear itself automatically every time it loses power coming in, then I can leave it as non-retentive. And in this case, we'll leave it as non-retentive. Okay, so I've got a timer that's going to time to 10 seconds. When that's up, I want to turn on an internal contact. Why is it internal? Because it's not directly wired to a real-world output, so therefore I'm going to pick an internal type bit. And I could pick a variety of different types. Remember, M's are maintained bit types, and T's are temporary bit types, both internal. I'm going to go ahead and use a T type here. I'll just start at 1, T1. All right, and I'll give it a name of, I'll just abbreviate here, motor starter 10 seconds. Okay, there we go. All right, so what's showing here is that we've assigned a timer, a non-retentive timer. Whenever the motor starter is not running, the timer will automatically reset to 0. Whenever the motor starter is running, it will count up to 10 seconds, and then as soon as it reaches 10 seconds, it will turn on this output by passing power flow. Okay, now let's do something with this contact we just programmed, this T1 contact. Let's make it into effectively another stop button, but an automatic stop button, if you will. So I'm going to go back up here, select normally close contact, put it in series, because that's what we do with stop contacts. Okay, double click on it, and I'll go ahead and call up the T1 bit that I just configured. All right, and now, after 10 seconds of running and the timer expiring, the motor starter will automatically stop. Now, normally, we would go into troubleshooting and debugging at this stage, but with the OCS, I think it makes sense to show you configuring screens next. Then we'll come back to troubleshooting. Let's learn about building user interface screens. Okay, to start programming user interface screens, we need to go to the Cscape Screen Editor, and that's available from a couple different locations. The easiest, for me at least, is to just press this little View Edit Screens button here at the top, and it pulls up the Cscape Screen Editor. Now, I can resize this window, I can zoom in and out, but it turns out that it's just about right for what I'm looking to do. So what I'm looking at here is an OCS screen. Now, what is a screen? Well, every OCS has the ability to be configured for a certain number of screens. I'm working with a Micro X4. It's good for up to 250 screens. Other controllers can do even more. Okay, so I'm on screen number 1, which has a little asterisk by it. That means it is the default or the initial screen. So this is the screen that is by default displayed unless You know, there's a reason why it's changed, whether the operator ends up changing a screen or whether the control program forces a different screen, whatever the case may be. But for now, I'm just going to go ahead and work with screen number 1. Now, if you remember the example we've programmed so far, it was just a simple start-stop circuit with real world start and stop push buttons. So let's just throw an indicator on the screen as a quick start. Okay, these are all the different graphic type objects that I can put on the screen. All right, and this is a text object. So if I wanted to put a title here, I could click on this T for this object, click and drag. So I clicked and dragged. Now I let go. Click again so you can see the size of the object I've created. All right, I want that to say something like start, stop screen or operator station, something like that, whatever I want to program. I'm going to double click on it and just type in operator station. Okay, it could be anything, just so happens what I want on this first screen. I'm going to center up the text. Let's go ahead and make the color red. Okay, let's make the font larger. Okay, and I'll hit OK. All right. All right, so that's more or less centered. I can also drag these out to make it more obvious that my text is centered. Okay, so I've got a simple title here. We've got numeric data objects. We've got a timer, time objects, a whole variety of different objects, switch objects, selector switches, sliders, jump buttons, bar graphs, etc., etc. I know I'm not spending any time on these objects, but again, this is a quick getting started guide. So we're going to start with an indicator, and that indicator is just the equivalent of a pilot light that we're going to use to turn on when our motor starter is running. Okay, so what I did there was I clicked on the indicator, I clicked and dragged to the size I wanted approximately, then I let go. Now I double click on this object. Okay, first step is to assign an address. Now, what address in the controller is going to cause this indicator lamp to light up or not? And that would be the motor starter, which I happen to remember was Q1. And you can see it populate here. Now, if I didn't remember Q1, I could, again, pull from this list of names and pick one from the list. But I remembered Q1, so we're going to make that as the assigned address for this indicator light. Now, by default, when this turns on, it's green. When off, it's red. I'm going to change that a little bit. I'm going to change the off color to be a dark green. Okay? Let's not do that. Let's make the on color bright red. Let's make the off color a dark red. All right, there we go. Now, if I hit OK, you'll see it says lamp. That's not what we want. We want it to say motor or run or something like that. So I'm going to double click and go back into the object. And under legend, I'm going to go ahead and select, let's just make this, motor starter. Let's just call it the full name. We can call it a bunch of things. All right. I'm going to leave the font as relatively small, hit OK, and OK. And we have a really basic two-dimensional looking pilot light. If we want to snazz it up just a little, give it some three-dimensionality, we can assign a 3D bezel to it. We can change to, let's just leave it as a round button, hit OK, and now it looks a little snazzier at least. Okay, so now we have an indicator that whenever the motor starter is running, it's going to turn bright red. When the motor starter is not running, it's going to stay a dark red. Now, how do I know more or less what it looks like when that happens? Well, I do have a little test button here, or operator simulator I can select. And then when I click, it'll show me what the indicator is going to look like. All right, I'll go back to my pointer. All right, now let's get a little bit interesting here. Let's say that in this case, instead of, or in addition to, a real-world push button that can start my motor, let's say that the operator also has the ability from a push button on the touchscreen to go ahead and start the motor. So I'm going to select a switch object. Okay, I'm going to go ahead and click it and drag it to approximately the same size, and I can change that later. Okay, I'm going to double click on it. And this is a parallel push button that's going to cause my motor starter to start. Now, this is not going to be wired to a real world IO point. So I would not assign a %I or %Q type register here or memory address here. I would use one of the internal bits because this is on off. So I could use either a T or an M, where the only difference between them is that the M's are maintained through a power cycle. Now that doesn't really make sense for a push button on a touchscreen. It makes more sense for that to be a T or a temporary bit. So I'm going to go ahead and select a T. Now if I select T1, remember I'd already assigned that earlier in my program. I don't want to reuse that one. I could either just go T2 or I could pick any other T. And frankly, I think with the micro series, there's at least 1,000 of them. But I'll just go ahead and make it T2. That's the next in line. And I'll name it while I'm here. I'll go ahead and call it Start TS for touchscreen. Okay? So when bit T2 turns on, which is going to happen when this button that I'm programming gets pressed, then when the button gets pressed, T2 is going to turn on. All right, down here under Legend, let's call this Start. Okay. All right, let's leave the size small. When we configure the switch, this kind of square gray looking push button probably isn't what we're looking for. Let's make one that's similar to what we did for the indicator. Let's make it round with a 3D bezel. And then under indicator properties, let's make it a little more interesting. Let's make when it's on, let's make it bright green. When it's off, let's make it dark green. Okay. All right, and that's just when we're pressing it, of course. All right. And we'll just say okay for now. Okay, that's kind of the basic operation. All right, so now we've configured a basic start push button. Now I'll go ahead and make it more or less the right size here. Now, one thing you may not have noticed is that as I'm stretching this, it's clicking. That's because Cscape has by default a secondary grid and a primary grid. The primary grid are these big squares. The secondary grid are the smaller gradients here, and I currently have the secondary grid enabled, which is why it's just clicking a little bit as I change size here. But let's go ahead and leave that alone there. Okay. All right, so I now have a start button and an indicator. Let's say we also, similarly, have a stop button that can also be operated from the screen. So let me, instead of creating a new one from scratch, I'm going to copy this one. So I'm going to hit right click and hit copy, right click again and hit paste, move it over to this location here. All right, double click on it. We need to give it a new internal bit because this is a different operator. Let's just move up to T3 and we'll call it a stop TS. And remember, we still have our hardwired push button, so this doesn't replace that. Okay. And under Legend, let's say stop. And then let's change the colors on the indicator. Again, let's make the center color. Let's just go ahead and make it bright red when it's on and dark red when it's off. We could make it whatever we wanted. Okay. All right, I believe we've got that fully configured now. Okay, so we've got a start button, which we've assigned to T1, or I'm sorry, assigned to T2. And if I don't remember what was assigned to it, I can hover here and it shows me. If I hover here, it should show T3. If I hover here, it's Q1. And the reason why this is Q1 is because this is the same bit that turns on the real world wired motor starter is the same bit that's going to cause this light to turn on. Okay, so that's why that does have a real world IO point. Okay, so we've just done this simple start, stop, and motor starter indicator. All right, let me go ahead and close this here and go back into our logic, and let's add in our parallel start and our series stop. So I'm going to click on my branch tool, click here and here, add my contact. Okay, and if I don't remember what this was, it was start underscore TS, I believe. There we go. Hit OK. And then I need another series stop button. I'll put it here. Anywhere in line would work. And this one, I believe, was T3. I could also pull it from the list like I did before. Okay, and now I have modified my logic to include operators from the screen, not just from real-world I/O. Okay, we've done our program, at least a little one here. Let's go ahead and download it into the controller. All right, and to do that, I need to make sure that I'm talking to the controller, which I am. In the lower right-hand corner, you see local 253, target 253. And then I have to hit the download button, okay? And it pulls up use smart load, which basically says it's going to download any items which have changed. Now, a lot has changed compared to the demo program that was running in here. So I'm just going to go ahead and hit OK, and the download process is starting. Now, the first time you do a download of a new program, that's when it takes the longest. It's got the most it needs to change, the most that is different from the previous version. On subsequent downloads, usually there's less that's changed, so the download goes quicker. Okay, well, the download's actually complete. Let's take a look at what's going on. This is a good time to learn about debug mode. This is the mode in which we can monitor our program and debug it. All right, so the way you enter debug mode is through this little debug button here at the top. I've pressed that. Again, you have to be connected and online with your controller. All right, and then where it's passing power flow, you'll see red, or at least the operators that are able to pass power flow are shown in red. And this is what we would expect to have happen, right? Nobody's pressed a start button yet. All of our stop buttons are allowing power to pass through them when the power arrives. And of course, the motor starter's not running, the timer's not timing. This is exactly what we would have expected. Let's flip over the OCS here and take a look at the screen. Okay, there we go. That's the screen we created. Wasn't the most sexy screen in the world, I will admit that. Okay, now, if I press that start button, we should see things happening. Let's see what happens. Press the start. There we go. Our middle operator has started. The motor is running. Our timer is also timing. And when it gets to 10 seconds, boom. Very briefly, too brief to even see, our T1 bit, motor starter 10-second bit, basically went off, which caused an automatic stop of the motor starter because that T1 bit, normally closed, was in series with the start-stop circuit. Okay, hopefully that will help you get started with OCS All-in-One Controllers.